Alright, today we're going to talk about another aspect of permutations. When we have indistinguishable objects. That means that we're accounting for objects that are exactly the same. So let's consider an example of this, just like we did with those wildcards, that we have some letters, there are 5 of them, and 3 of them are B's and 3 of them are C's. Okay, I'm going to go to full screen. So we're going to consider the letters B, 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 C, C. So we can arrange them in a certain number of ways. But if we see what starts to happen, B, B, B is the same as B, B, B. That sounds kind of funny to say, but this is really what we're dealing with. And so dealing with permutations of indistinguishable objects is going to be about finding the total number of orders and dividing it by the number of ways there are to repeat those orders. So what we're going to start out with is we are going to assume that B, 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 C, C, C has a certain number of ways to order them. Well, there's 5 letters, so there's 5 slots. So we have 5 times 4 times 3 times 2 times 1. And so 5 factorial is the total number of orders. But what we need to do in order to see how this works is assume that the letters are all distinct. And so this is one order. But if we consider the fact that we could arrange the orders of the B's, we could have B1, B3, B2, C1, C2. Or we could have B2, B3, B1, C1, C2. Or we could have B2, B1, B3, C1, C2. Or we could have B3, B2, B1, C1, C2. Or B3, B1, B2, C1, C2. That's if we just move the B's. So there are 6 orders for just the B's. Okay? And if we think about what that means, we have 3 B's. So that would be 3 factorial ways to arrange them. So if we consider the fact that we have the C's, there are 2 C's, so that would be 2 factorial ways for the C's. And so what we're going to do is we're going to take the total number of orders, which is 5 factorial, and divide by the number of repeat objects. Okay? So what we're going to say is this. To account for repeats, we're going to take 5 factorial and divide by, so this is the total number of permutations. And we're going to divide by 3 factorial, which is the number of orders for just the B's. And we're going to divide also by 2 factorial, which is the order for just the C's. Okay? That's going to account for our repeats. Notice the bottom total, which is 3 plus 2, is the same as the top total. 3 plus 2 equals 5. Okay? Everything that's accounted for on top is also accounted for on the bottom. Okay? That's how we account for repeats. In general math language, the number of permutations of n objects, where r is the number of types of objects and k is a set of identical objects, so the B's or the C's, is going to look like this. N factorial over k, the first object factorial, times k2 factorial times k3 factorial, all the way down to k, the number of repeat objects we have, where k1 plus k2 plus k3, etc., plus k to the r is equal to n, not even the factorial. Okay, so all of the objects on the bottom have to equal what's on the top. Let's look at an example of this. If we have dice, which are also called number cubes in math class, which is what I learned in college, we have 7 identical dice are rolled. Find the number of ways that 2 4s, 1 5, and 4 6s can be rolled. Whoops, forgot the E on 1. Okay, so we have 2 4s, 1 5, and 4 6s. It would look like this. 4, 4, 5, 6, 6, 6, 6. The total number of ways is equal to 7 factorial, because that's the number of die that we have, the number of objects that we are rolling. But we have to account for the repeats. If we account for the repeats on the bottom, we have to consider how many objects we have. We have 2 4s, so that's 2 factorial ways that we have to divide by. So I'll put that on the bottom. And we have 1 5, so that's 1 factorial ways. So I put 1 factorial. And we have 4 6s, so that's 4 factorial ways. So I divide by 4 factorial. Notice we have 7 factorial over 2 factorial, 1 factorial, 4 factorial. All of the numbers on the bottom add up to the top. 2 plus 1 plus 4 is equal to 7. And so when we actually calculate that out, we end up with 105 permutations. The identical objects, we divide by that number factorial. Okay? Let's look at an example using coins now. We have 8 coins that are stacked. There are 3 pennies, 2 nickels, and 3 dimes. We have 3 sets of objects that have duplicates. Okay? And so when we talk about having no restrictions, we're saying there's no reason why any of them have to be stacked together. And so that would be like we would normally calculate a problem. So we have 8 factorial total different ways to stack all of them, and then we have to account for the repeats. Well, in this case, we have 3 pennies that are the same, so that's 3 factorial ways. We have 2 nickels that are the same, so we have to account for those. And we have 3 dimes that are the same, so we have to account for those. So this is with no restrictions. I'm not necessarily concerned about the number on this one. Okay? Now, here's a restriction that throws a little bit of an interesting wrinkle into the problem. What if the dimes must be stacked together? So here's what we're looking at. We have a stack of 8 coins. And part of the restriction here is we're thinking we really have 2 distinct stacks. There's the 3 dimes. And there's the 5 other coins. Well, if we think about the dimes as being a package deal, the dimes there's only one way to stack those 3 dimes because they're all identical. Okay, so the dimes are identical, so there's really only one way to stack them. Because if we think about this, it would be 3 factorial for the total number of ways to stack, divided by 3 factorial for the number of repeat objects. Well, that really just equals 1. There's only one way to stack it. But if we think about those 5 other coins, really what we're dealing with is we have 5 factorial ways to stack those, but they have repeat objects. So we divide by 3 factorial for the pennies and 2 factorial for the nickels. That gives us 10 ways. But if we consider the fact that we have 5 coins, and those 5 coins, I'll draw another stack over here, 1, 2, 3, 4, 5. This stack of dimes could go here, could go here, it could go between these, it could go between these, it could go between these, and it could go on the bottom. So there's 1, 2, 3, 4, 5, 6 ways, 6 places to put the dimes. So now we have 10 possible ways to stack those 5 coins and 6 possible slots where that dime could go in between. And so really what we have is 10 times 6 is 60 ways to stack. Okay, a little bit tricky there, guys, but all we did was use the counting principles of accounting for repeat objects and figure out logically where we could possibly put that restricted stack. Okay, thanks for watching, guys. We'll see you next time.